quadrants or incremental encoder. Well, what's an incremental encoder? Not very impressive, guys. What is an incremental encoder? By this time you could have Googled it and probably told you that. An incremental encoder. So what we're doing is we were looking at position sensors, right? And we looked at a potentiometer, right? We went over the line and looked at what potentiometers we have over there. And we have two. We have the robot on the right on the Amatrol line, the gantry robot, the one on top, has a potentiometer on it, a linear potentiometer, so it's not rotary, it's linear. And then the one on the Festo line has one on the testing, I call it the testing station, because all it's doing is checking to make sure the thing's at the right height. So the potentiometer, what does the potentiometer give us? As a position sensor. Well, when we say gives us, we don't use potentiometer to see if there's something there or something not. That would be a proximity sensor. We're talking about a sensor. Now, what does a sensor do? What does a sensor on that manufacturing line do? It converts a physical quantity into a proportional electrical quantity, if it's an analog signal. If it's a digital sensor, it supports a physical over a true or a false. And then we can process it. Now, our sensors have got to convert it to electricity. So what two forms can it put it into? Either what? Two, it's got to get it to electricity. Digital could be me turning this thing up. Here's a 1, here's a 0. That's digital, right? You understand? So we can't say digital. It's going to convert it to either, we got three quantities that we always deal with in electricity. What are those three quantities? One of them starts with a V. Voltage, current, and resistance. Okay. So that means this potentiometer has got to give me an electrical signal. It cannot send resistance. Can it? So there's no sensors. That the sensors might vary a resistance, but then we're going to take that and convert it over to a what? A voltage or a current. We don't like a lot of current in sensors because sensors create drops in wires, right? So the predominant method we use to send it is varying or what? Starts with a V, voltage. So that's what a potentiometer does. A potentiometer gives us a voltage that's proportional to wherever that thing's at. So if I had 10 volts across A and C, this sucker would give me something between 10 and 0. So if it's 5 volts, it would say, okay, if it's 360 degrees, it says, okay, I'm at what, 180 degrees. Or I've moved so far. Right, you understand? So 5 volts might be, it's moved 6 inches. Right? And if I measure 10 volts, it would mean it's moved 10 inches, right? You understand that? This is only a single turn pop. We get about 350, 320 degrees out of it because we got to make room for this wire that goes into what we call a wiper. This is just a carbon path around here. And what happens is the wiper's got a little contact on it, and it just slides across that resistor. So every sensor that we've got on that manufacturing line is going to provide some voltage that indicates something. Right? Don't understand that. This would be an analog sensor. In fact, I've got it on the power pin. So this is going to give me a voltage that's proportional to wherever that wiper's at. Now, we don't show that, but we could just as well take that resistor and spread it over like this, right? And then we have a wiper coming right here. You'll understand that. And as it moves across this thing, this is what we call a linear pod or a straight line pod. That's what's on this, on the gantry robot on the right of the ammeter line. Across the top over there, that's a linear potentiometer. The one over on the Festo line, I don't know what it is. I mean, it might be linear. It's a potentiometer. It might be linear. We move it in a linear motion, but that don't mean the potentiometer is linear because it could be, like we said, we called it a rack and pinion, right? What does a rack and pinion do? It takes a linear it's a gear assembly that takes a linear motion and converts it into rotary, or takes rotary and converts it into linear. For years, guys, this is the way we drove our cars before we used hydraulics. A rack and pinion, because you turn your steering wheel like this, right? And then we have tie rods that went across that would do what? That would turn the wheels left to right. Go-karts still do it that way. So I don't know what the other part is. So we have one gear that's laid out. It's like this, right? And then we have a rotary gear that meshes with this. And then after as the gear turns, this moves. So I could take this and move this, and turn this, and it would cause this to move back and forth. Or I could take this and move this, would cause this to do what? Change directions. So when you see a linear pod, if it's a bigger assembly, you don't know if it uses a rack of pinion or something like that. That makes sense? So a potentiometer as a sensor. Now we use potentiometers for a lot of different things, but as a sensor, we're going to get a voltage off of it that's proportional to its position, right? So that would be proportional to wherever this guy's at. And then we would take this and connect it to whatever we want to sense that's moving, right? You understand? So this might connect to that mechanically, right? So when that linear thing moves, it's going to turn the rotor on the pod. It's going to give us a voltage back. Now we would have to scale it. We call it a transfer function. So we would have to scale it and say, okay, this many volts equals this many degrees. And so you'd have to do a little math. What most of your PLCs support now is a scale function. So you can bring it right in off these analog devices, and you can convert it to a binary number that represents that position. And we call that scaling, by the way. So these are our encoders we just talked about. So we have an absolute cut. Well, let's look at this. So this has got 4 bands. And as we move, what we have, so this is the way we count in binary, and we'll just use 4 bits. And I'll have to make a little room, because with four, so the digits in the binary numbers, we don't call them digits, we call them bits. And then with a group of 4 binary numbers, anybody had that class, what do we call a group of 4? What? It's called a nibble. And then a group of 8 is called a byte. Yeah. And a group of 16, we lose the feeding frenzy and we go to a word. So a group of 16 bits is called a word. And then we say a double word, a quad word, right? You understand, to move these things. So when they talk, and I hate that when they talk about gigs and megs. You know what gigs is? Could be gigahertz. It's bytes, that's what it is. In memory, it's gigabytes, but people don't say that. They say your phone's got 8 gigs of memory. So most people know the more gigs it's got, the more applications you can install, right? But it's actually bytes. So memory capacity is laid off in bytes. You know, in binary, what's a K equal to? 6 to the 1024. And then a meg is equal to 1024K, which gets people confused too. So it's very interesting. So I'm going to do nibbles up here because that's what we got. We got 1, 2, 3, 4 bands. So if I started counting, that would be 0. Now the way we do this, this goes 1, 2, 4, 8. That's the decimal weight of these binary bits. And then what would the next one be? What would you think? 1, 2, 4, 8, 16, 30, right? 16, 32, 64, 128, 256, 5, 12, 1024, 2048, 4096, 8,192, 16,384. You'll see I've been dealing with binary a long time, right? So this would be, if I look at, all we do is look up here, right? And there's a 1 in the 1 column, so that's 1. Right? I come over here and put the next combination. What would that be? 2. I come over and put this. That would be a 3, because that's 1 plus 2. That makes sense. So this would be a 4. I might have to, this would be a 5. This would be a 6. This would be 7. This would be an 8. This would be a 9. This would be a 10. This would be 11. This would be 12. This would be 13. This would be 14. And this would be 15. So there's our 16 combinations, including 0. So what that means is every one of these we have these sensors right here. They're usually optical. And as this thing moves, it either lets the light come through or breaks it. And then what we would do is if it's at the 0 position, we'd get that back from it, right? You understand? In voltages. So all of the outputs would be 0. Over here, this guy here would give me a voltage. So now my PLC or whatever I'm running would know I'm at position number what? 1. If I got this back, we'd know that the device was at position number 2. If we got this back, it would know that it was in position number 3. Now, all we knew is that how far are these positions apart, right? You understand? And the more we a term called resolution. I don't know if that's in y'all's glossary or not. It ought to be. So when we talk about sensors and stuff like that, what does resolution mean? Y'all ran into resolution all the time when you talk about your TV. When they talk about your 1020, what is it now? 1024, the resolution. We know the more pixels we have, picture elements we have, the sharper the picture is, right? So resolution means how precisely we can do something. So if I took 6 feet and divided it into, that's not 6 feet. If I took, what's that? Close to it. If I took 5 feet and had only 16 positions, our resolution will be very small, right? You understand? So what I would have to do is I would come up here and maybe add another bit. Well, if I added another bit, then we would have 32 counts over that resolution, right? But I would have to add another track to my encoder, and I would have to add another sensor. Well, if that wasn't enough, then I'd have to add another track, right, and add another sensor, and add another track, and add another sensor, right? So if I had 1024 positions, then I would have to have 10 tracks that I would have to keep up with. Either the sensors are going to have to get smaller, right? You understand, or we'll just have the thing will start getting bigger. Now this is a linear absolute encoder. Now the advantage of a linear absolute encoder, like we talked about last class, is if we turn the system off and turn it back on, it automatically knows exactly where it's at. because that encoder is not going to move, right? That makes sense? So we can read this anytime. The other more widely used encoder, because of its cost, is what we call an incremental encoder. All this does is just give us pulses. And each pulse would represent a position, right? You understand? So we come over here and we put two optical sensors, but they're located, and we'll go over there and see. We can't. That's why I wanted to bring the other one we got, because I can't change directions on the one on the manufacturing line. But what is, each one of these pulses would represent a position. Now we got two options. We could use one of them as the position, or we could actually use two of them. So we could get, if we look at just edges, then we could count the edges. But what we have to do with this, guys, we take the output of this and we run it into digital counters. And then these counters are going to count digits for us. Does that make sense? So with one pulse, these things would count one. Second pulse, they would count two. And then what we do is we come out and all we have to do now is just read the counters. Now what the advantage of this is these counters are integrated circuits. So we could have a real high resolution, right? Does that make sense? With still very little hardware. What's the disadvantage on this, the guys up there? So I turn my machine off. As soon as I turn my machine off, these electronic counters are going to lose their game. Start all over. And I turn it back on, and the counters say they're zero, but my piece of equipment is out here somewhere. Right? You understand? So what we have to do, one of two things, what the robots do, is they keep these counters, they got batteries inside of them. So what it does is it keeps the watt. It keeps the count even when I turn it off, when I turn the thing off. And the batteries are inside the robot, because if it didn't and I had to lock out the robot, as soon as I killed it off, I would lose my count, and the robot wouldn't know, and the controller would not know where that robot's at. So the controller is the computer, the robot controller is the computer that keeps up with all these counts, right? You understand? We kill power, then we kill power to lock out and tag out, then what would happen? Then the controller would not know where the robot was at. So none of the programs that you have written would do what? It wouldn't run. The robot wouldn't let them, the controller wouldn't let them run, because it says, hey, I don't know where this sucker's at. I don't have any idea. Now you can still go out there, and we call it jogging the robot. You can manually move the robot, but you won't run any programs. Because manually moving, you're looking at the robot, right? So the controller doesn't have to know where it's at. It's you that's controlling the position of the robot. Or, like your printer or something does, it has a sensor over on one side. It's usually the left-hand side. The left-hand side. And every time you turn it off and turn it on, what do you hear it do? Well, what it's doing, it's coming over here and finding there's a sensor over here that it touches, and it says, okay, this is zero, right? You understand? And after that, it what? The controller knows where it's at. So we either, one or two things with incremental encoder, we always start it from a known position, right? Or we put batteries on. The batteries, we still might have a problem. So if you work with a plant with a bunch of robots, and one of the preventive maintenance things would be go out there and change those batteries out of the robot. Usually it's recommended, some do it 6 months, a year would probably be good on most batteries. If you leave your robots on 24 hours a day, then the batteries are not used. The only time the batteries are used is when you do what? You turn the controller off. So these are incremental encoders. We actually get a number back from this thing. It's not analog. This is digital. So the inside of this computer is digital. Everything it knows is digital. Everything it knows is ones and zeros. So that means if I bring an analog sensor into my programmable controller, which is digital, right, then we'll have to go through a secondary circuit called an analog to digital controller. So, you know, so 3 volts might equal to that count right there. It don't have to equal to 3. It could equal anything depending on the span, right? You understand? So what we would have to do is take that into an A to D converter. It would look at this and convert it over to a binary number that represents that. And then we would scale it according to what we needed, right? You understand? So now we would have to say, okay, a count of 4 equals 6 inches. And that's what we call scaling. In sensors, we'll call it a transfer function because that's the way I learned it. So you would come up here and you'd say, okay, I get 5 volts, right? So this would be out of the sensor. So let's say 10 volts. And then I'm measuring degrees. And let's say my sensor gives me 360 degrees. Well, what we would get now, so what's 10 divided by 360? 10 divided by 360. You're going backwards. You're taking... Now this is volts, so my answer is going to be in volts, right? This is degrees, so my answer is going to have degrees in it. Those don't cancel each other out. So what would I have? Maybe it's a milli or something, right? Because they were taking 310 divided by 360. Okay, so 27.7. We might even carry out for, and this would be millivolts per degree. Per degree, Rich. So now if I know that, if I'm getting 5 volts out, I would multiply it by that, and it would tell me the actual angle that that thing was at. We could just well says 10 volts equals to 360, right? You understand? Or we could run it and say, okay, 7 inches equals to that number right there. And then I could calculate the scale of the transfer function so my display displays 53 inches, right? Understand? So this is what's nice about these guys. That would be inchometer. This right here, I don't have to do this, but this is going to give me this. Right? You understand that? If it gives me that, now all I've got to do is scale it, right? You understand? Where that number equals to some distance. Now, what this guy here does is that depending on, now notice the sensors are offset by 45 degrees. So what happens is that when it's moving in this direction right here, this guy would occur first. If it's moving in that direction right there, this guy would occur first. So depending on the offset, we can tell the direction this guy's going. So that means we could tell our counters either to do what? Count up or count down. When you take sensors, we would actually show you the circuit. The basic circuit can do that, but we don't need to understand that. So we have what we call up-down counters. So what would happen is we'd have a sense that says, okay, if this one occurs first, count up. If this one occurs first, count down, right? And now we can move what? In both directions. So the robot's got to have that. Robots are moving in, even though we got a quadrature encoder on the manufacturing line, on the Amatrol line, it don't need to be a quadrature encoder. It is because that belt only runs what? In one direction, the conveyor belt. So this is an absolute encoder on the right. This is a quadrature encoder. So this guy here's got 1, 2, 3. Right. 1, 2, 3. He's got every number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that 11, right? That would be 2048. So it could split one revelation into 2048 if I didn't miss one. So this would have a pretty good resolution, right? And then what they do sometimes is they'll make one index mark for every revolution. So what we could do is that would indicate, so an incremental encoder, we could get one pulse per revolution too, right? So the robots usually have that. The robots are, we'll go over there and look at it. So we can see the incremental encoders on the robot and counters and everything. So limit switches, we'll go back and try to find all the limit switches on the manufacturing line. These guys have been around for ages. And like I said, even though they're a proximity sensor, over time what has happened is limit switches have their own name because they've been around so long. When we use the term proximity sensor, we're talking limit switches are what we call contact sensors. What does that mean? It's a contact sensor. What does it mean? Yeah, it's got to make physical contact to the thing it's trying to position, figure out what's at a certain position, right? Okay. So these guys, and we have several symbols, by the way. And this is also true on, and we'll look at some of the schematics for the PLCs. Now what we do, guys, is we look and see what gravity is doing. So gravity's trying to open this thing, so this would be what we call a normally open limit switch. And then we'll come over here. If I drew this like that, that would be wrong, right? You understand? Because we would call this, no, we would call this a normally open being held closed. Because gravity's trying to open it, right? You understand? So it must be something. And normally what we do is we draw these limit switch at the device's home position or its origin position. So if it's got a limit switch that indicates it's up against that where we park it at, then when we turn it on, it's going to be closed, right? You understand? So in your diagram, it would be drawn like this. This would be a normally closed. So I'd come up above it, right? You understand that? So gravity's trying to close it, so it's already closed. So this would be normally closed. And then if I come over and solve this, then this gravity's trying to close it, right? You understand? So something must be doing what? Holding it open. So this would be normally closed. And these would be the symbols that you would see in your diagrams when you go there. So you need to know that because if something happens and you have to replace that limit switch, and you say, okay, that's a normally closed contact, and you wire normally closed contact, then you screw the whole system up, right? Nothing really works. So you need to know those symbols, right? Everybody understand that? And we'll do a lab this afternoon, even if they don't show up. I mean, we'll do a lab here in a minute. These are called heavy duty. These is what you'll run into in industry most often. We use these electronic duty limit switches over there, which are not designed. So a lot of these heavy duty or industrial duty type limit switches, you can literally run loads off the limit switch. So you could run a motor off the limit switch. These guys are basically designed to send, first they're really small, and they're used just to send voltage into a PLC. And then let the PLC control the relay, right? That controls the load. All right, we went back and looked at that. Everybody okay? Yes? Okay, so we'll come back. We have magnetic field sensors. we doing? We're not taking a break. No, we're gonna take a break at, I think I didn't I say the time? Uh-huh. Then we'll get out 11:30, hour and a half. Lower Morrison. Man, that reed switches. I'll go get some of these. What we do we know magnets do what? So magnets that are opposite polarity, so north to south, what would they do? Would they repel or attract? And attract each other, right? And then like poles do what? Repel, right? Understand that? Like poles, like south to south, or north to north, cause magnetic fields. So these are some magnets. Didn't want to do that. I think I'll just have to look at this upside down. So, these meter leads, so we're actually getting where they're putting a category on the meter lead. So this says this is 1,000 volt Cat 3, 600 volt Cat 4. So what type of voltage spike it can handle, we would have to go back into the chart. I'm sure after a while you would learn it. But so the maximum range, if you want Cat 4 protection, maximum range you should put your meter on with this lead right here would be 600 volts, right? But you'd have to have a Cat 4 meter. This is not a Cat 4 meter. This is a Cat 3, 600 volts AC, and AC or DC. It's Cat 2, 1,000 volts DC and 750 volts AC. So I can, even though this has got a Cat 4 rating. Now the problem is that rating is with not that metal rod. Let me get it over so you can see it. Let me put it full screen. So it's with this metal rod out here covered up. So what you have is you come over here and get that for me. Would have this cap on it. As soon as you expose that thing, then the category, you'd have to drop the meter leads down one category. Right? You understand that? So I'm going to put these boots on there. They'll have people that'll take the boots, pull them off, get to the alligator cliffs. So what I'm going to do is I'm going to take my black lead and put it on one end of my and I got my meter set to ohms. I'm not on. I'm gonna put it on. So we got it set to continuity. So if we touch the leads together, it beeps. So that means we got. What does continuity mean in electricity? Huh? Or little or no resistance is what's central, right? Don't necessarily. When you say complete circuit, it just means you have little or no resistance between the two leads. So I could put it anywhere in the circuit, right? So we have it here, and then I'll get my magnets. Magnets. And if I approach it like this, of course nothing's going to happen. If I approach it like this, nothing's going to happen. Or if I change the other polarity, nothing's going to happen. So what I'll have to do is bring it up here from the sides. See what I'm doing? This right here doesn't work because it's got to see a north-south or a south-north. To concentrate through these metal rods in there, concentrates through the rods, and you end up with a north-south or a south-north, and what do? They attract each other. So if I bring it like this, because then, very simple. Like I said, you can get them big. So this guy, how big they are would depend on how much current they control. So the size, switches and contacts and fuses are rated with two things. What's the two things we rate those things? What's that? Amps. What's the volts? Well, the volts is the push, and we're trying to break a circuit. So the further we spread those things, the more voltage it can break, right? You understand, the closer they're together, the less voltage we can break, because if you create an arc, you get ozone, and they'll start arcing. And then, of course, and also we're rated in current. So the bigger these rods are, the more current they can handle. Well, PLC inputs, we're looking on the range of milliamps, right? So those things can be what? Little bitty. And some of them in that tray, they're pretty small. Are we okay? So this is what we call a magnetic reed switch. Most people just call it a reed switch. Very simple. Now what's the cons of this? What's the problem with this? It's cheap. That's the pros. It's cheap, right? You understand? So what's the cons? What's the disadvantage? Right, because it's electromechanical, right? It controls electricity, right? So like these guys could pulse and something can happen, and if I create an arc is like 32,000 degrees, it'll melt them contacts together in an instant. And then these guys you throw away. Relays you could break apart. But these guys, once they welded together, you got access to them, you might beat them, break the glass. But, so they're electromechanical, or they could fail mechanically, right? Something could happen up here where it wasn't made exactly right, and one of these arms could break off or something like that. Or they could get shocked and they get bent out too far, so they don't get enough motion to do what? Make contact. So these are electromechanical devices. So that's the biggest problem. But what advantage does it have? Cheap. The cost. They're cheaper than a solid state, or one we'll look at next, which is a Holotech. So the Holodeck sensor is an electronic sensor that senses the strength of a magnetic field. That's all it does. The strength of a magnetic field. Huh? Yeah, you have to create that magnetic field. That's what we was looking at over there. This is what we was looking at right here. This is a standard magnetic. This is a pneumatic cylinder that's specifically designed to run with either a Hall effect sensor or a magnetic reed sensor. In the piston, they got a what? They got a magnet. Or you got a burglar alarm in your house, and you've got sensors on your windows to keep people from opening. Well, the moving one is a magnet, and the one that mounts permanently, which has to be the electrical power, is a reed switch. That's what they use in burglar alarms. These things you put on your box. So all we got to do is just attach a magnet to whatever we want to sense the position of. If I've got magnetic devices, then we don't need that. But it's a non-contact sensor. That's a big advantage, non-contact. The problem, anytime we bring two things in contact with each other, we create friction and they wear out. So that operator on that limit switch is going to have to be replaced sooner or later because it makes physical contact with something, right? You understand? Now, sometimes they'll put rollers on them and try to limit that, but they all go bad sooner or later. So a limit switch will go bad, what? Sooner or later. These might go bad, but, you know, odds are these will last longer. We don't have to worry about friction, right? You understand? Because they what? The magnetic field and the sensing element are not actually making contact with each other. So a Hall effect sensor doesn't sense metal. All it senses is magnetic field. And so you notice this is some things they do where they appear to sense metal, right? You understand? Where they appear to sense metal. On this one down at the bottom, they have a magnet behind the Hall effect. So when that metal ball rolls across that, it concentrates the magnetic field. The Hall effect is not sensing the ball, right? It's sensing that magnetic field did what? Change. Here it's sensing the tab in a rotor, right? So that means when this thing spins around, it would and the magnetic field is on this side over here, right? You understand? And then it rolls around, it would get a little pulse, a little dip every time that little thing came around. So that's all it does. This is what we were using it for, is we're just using it to sense when the magnetic field comes across it, right? You understand? And that's the way the cylinders are working. So we mount the Hall effect sensors out there, or we mount the magnetic sensors out there on the piston where we want to sense they are. If you notice, we can mount sensors all up and down those rails the way they're designed. So we could sense when it's like halfway, or we could sense quite a few things, right? You understand that? Well, this is solid. We're not talking about that thing you're holding in your hand anymore. This is a electronic sensor. This is solid state. It's sensing the magnetic field electronically. So we don't have contacts inside these guys. We got some type of electronic device that either simulates an open contact or simulates a closed contact. But these guys only sense magnetic fields. But what's nice about this, that guy, that reed switch has got to have a magnetic field of a certain strength before it does what? Before it senses it. These guys right here are pretty good. These are pretty good magnets. No, well, it's causing it to become true. It's causing it to go true or false. There is no switch in it. You're holding that thing in your hand, looking at it. That's not a Hall effect. That's a reed switch. A Hall effect is an electronic circuit. It's a 3-wire sensor and not 2-wire. That's a 2-wire sensor right there. That does not have to be powered up. As soon as I say solid state, it would mean I go out there and disconnect my battery and go turn your radio on. What's your radio going to do? So it's electronic. It's solid state. Before it does anything, it's got to be what? Powered. So it's at least a 3. So we can get 3-wire sensors and 4-wire sensors. So these we don't have a contact. We got a device that simulates a contact. We call them bipolar transistors. We saturate them and then they conduct current. But so the magnetic field don't make any difference, right? You understand? Well, on the latching it does. We'll have to look at that, which is really cool, the way it's designed. But these could be, but the problem, what's nice about this guy is it's solid state, right? Which, when we say that, it means no moving parts. So that's the biggest advantage. So it's electronic, so your reed switch is going to have to be a certain size. So those big old metal ones mounted on the side of those cylinders are probably reed switches. On the cylinder that pushes the block out, the little tiny sensors, them are probably what? Them are probably Hall effect. So electronics can be what? A lot smaller. So these are Hall effect sensors, and they could probably be smaller than this on my circuit board. That right there is a Hall effect sensor. Could I make a switch? Could I make a mechanical switch that small? No way. Right? You understand? And handle any current. So these are two Hall effect sensors. These little things right here. And they got 3 leads on them. Why do they need 3 leads? 2 of them going to be power. And then one of them's going to be the signal. One of them will, these are DC. So depending on how you power them up, we'll look a little bit at the data sheet. These things I can operate, I think they can operate from 5 volts up to 20 or 30 volts. Most of the time in PLCs, when we use DC, we deal with 24 volts. So that means if it detects the magnetic field, it would give you 24 volts. If it didn't detect it, it would get what? 0. Or vice versa. This guy right here is a little different. I have to figure that out. But that's a Hall effect right there. It can't sense metal, but we can simulate it because we know metal concentrates magnetic fields, right? You understand? So coming through here is what we're saying, okay, it's sensing a metal ball. Well, it's not sensing the metal ball. It's sensing when the ball rolls across that magnet, the magnet concentrates the field through the ball and causes that Hall effect to sense the magnetic field change, right? You understand? When this thing right here is flopping around right here, it's going to get a little dip the Hall effect is going to output a little dip every time it makes a rotation, right? You understand? Or we could use a magnet. So, in our cylinders, we have magnets inside of them. So now we can use either Hall effect or we can use a what? We can use a magnetic reed to sense where that's at. What are they going to use? Well, it's up to the people who get there. You know, fluid power, we've got some switches that simulates a reed switch. It really does. We've got some magnetic switches over there. If you take fluid power, hopefully, when Allison teaches it, she shows them those things. And you strap them on the side of the cylinder and you put a pneumatic hose into it. And when you put it there, it closes the valve or opens the valve to let the pneumatics go through. So that would be a reed switch. That'd be an example of a reed switch, but it's controlling another power source except for the size of electricity. So magnetic reed switches, we can't make them really small because they're electromechanical devices, right? And we have to compensate for the size of the magnet. But these Hall effect sensors, they can be extremely small. But they don't sense metals, right? What do they sense? They sense a magnetic field. And we have 2 types, guys. We have what we call we have a latching type, which means the way these guys works is one polarity will latch it. One field pole would latch it, and it would stay activated. I could put it there from now to doomsday. So if a north activates it, I could put a north up there, and its output would switch on, and I could put the north on there forever. What does it do to have to unlatch it? You have to put a south pole in there. And then we have an analog over here, which will give us a voltage that's proportional to the magnetic field. What's really neat though, it'll go one way when it's north and one way when it's south, which is pretty neat. I'm trying to figure out how I got this thing wired. Oh, I must have closed now, y'all. So this is a latching Hall effect. an HI300. So this is a switch. So this is latching. And these are your 3 wires. So pin 1 would be what? Your positive power supply. Pin 2 would be your ground, and then the output would be pin 3. That's that right? Very simple wire up. And then the other one is a linear.
So the pins are way over the switch?
No, they're not. Watch, it's pretty standard on these packages. The package is in the shape of a D. So if you looked at it from the top, it looks like this. And so what you do is you face it from the one that's in D. And it says, if I'm looking at it from that direction, the first one on the left is what? 1, and then 2, and then 3. So what? First of all, if you guide it, if you get the part number on it, it will probably show you how that is. But you're not going to see a Hall effect from this. What you're going to see is you're going to see it from a sensor point of view, right? So it's going to be mounted in a sensor. So what we do is we have what we call standard color codes that they use. So what it is brown. Brown is positive. Then blue is negative. And black is your signal. That's a 3-wire sensor. Now, if it's a 4-wire sensor, which a 4-wire sensor simulates a single pole double throw contact, a switch. Y'all know those names, right? Single pole double throw. Are you okay there? Okay. So a 2-wire sensor usually simulates. I haven't seen one that comes normally closed, but I'm not going to say you're not going to run into it. But a 3-wire sensor would simulate a single pole, single throw switch, normally open. And then a 4-wire sensor would simulate a single pole, double throw switch. And one of them, the normally open, I think is black. We would have to do that. And then they'll add a 3rd wire, and it'll be white. So 4-wire sensor would have 4 wires coming out. But and then power would be what? The power of the sensor. We would have what? Brown. This is DC, by the way. This would be plus. Then your blue would be common. But you see people use the term all the time, misuse the term ground. I mean, it's all over. So I drew both switches in one thing, but that should be right. And this is a standard color code, and then it's this one. So that would be a 4-wire system. Yeah, and that's what gets us confused, because usually over here, if you did a lot of house wiring, normally here in DC, we like to use red for plus and black for minus, right? But they don't in sensors. Sensors, the brown is the plus, the blue is the common, and then your black would be your signal. But we could go over there in a minute and we'll look at these sensors, and we'll see how they're wired up. You'll see all the browns are going to be going. All the browns are going to be going to plus, and all the blues are going to be going to what? Common. So a common can be grounded, but a common doesn't have to be grounded. But most people, don't understand that. So like your car, they'll call the black wire the ground wire, and that's not true. That's a common. Your car has a common. It don't have a ground, right? But everybody calls it ground. If you walked into AutoZone and says, I need a wire for my common on my battery, they'd say, what? They'd say, how many doors does your car have? They had a place down here in Bessemer called Mulkins, and I lost one of the rods on my 55 Chevy. And when I walked in the door, The guy saw me coming. He says, "That looks like a so-and-so off a 55 Chevy when I came in the door." You go into AutoZone now and you take that thing in there and they'll say, well, and it's mechanical, right? And they'll say, how many doors? I'll say, how big's the engine, right? How many doors does it have?
I guess that's a default question they ask. They ask about everything.
Well, that's what they have to do to enter it in so it'll come up and bring it up. So, what they need. What year is it, right? What model? How many doors does it have? They want to know how many doors it's got. 2 doors or 4 doors. Well, you know, those guys. Yeah. Well, I don't know if y'all remember Mulkins. Anthony might. Used to be downtown Bessemer. Mulkins and then what's the White's is still around. Yeah, White's I don't know if it's in downtown Bessemer. It used to be right by the library now. And now, but it's out here on 19th Street. Yeah, 19th Street. It's on for Utah. But I got 2 stores. So what I'll do is I'll do this while y'all out on lunch. But let's go back here and see if we can find our magnet. Or we'll look at and we'll look at both manufacturers. And then what we look at is electrical characteristics. So this guy could be anywhere minimum of 4 volts, maximum of 6 volts. So this guy's got a real wide operation range. But you can't power it on 5 volts and expect to get 24 volts out, right? You understand? You'll never, ever get what you powered up. In fact, if you put 5 volts on it, you're not going to get a 5 volts out because that would say the thing would be 100% efficient, right? That makes sense. We're powering it up on 5 volts because we're running what I'm doing on the signal output. So that's the actual block diagram of the whole sensor itself. This is what we call a sinking sensor because this guy, that's the actual guy that's simulating a close contact. But what it's going to do is it's going to take this lead and connect it to the common. So that means the way I would have to hook this up is I would have to have my load up in here, right? And then it would go to power, which we technically call sourcing, but we'll talk about that when we get into PLC. But that's the guy right there that's simulating our contact. There's only one on it, and it's acting normally. But this is all the stuff that goes. Of course, I don't need to know that, right? So when we look at our camera, this guy right here, and I've got a circuit connected up, and I've got this LED connected to my output signal, and then I got a magnet, I got power on, so I can tell which is north and south. So south turns it on, north turns it off, right? Because normally when you get a magnet, you have no idea which is north and south. All we know is likes attract and unlikes repel. But here I'll come in with this direction, and it didn't turn on. I'll come in from this direction. So this turns it on now. It's going to stay on, right? Yep. Because so that's a south pole right there. So a south pole turns it on. A north pole is required to turn it off. So what I'll do is I'll flip my magnet around, so that turns it off. That turns it on.
What's that right there?
What's that? This is a resistor. Now we can't put an LED in the circuit by itself normally because I'm putting 5. If I put An LED, on diodes, we have what we call it only lets current flow in one direction, but we don't use LEDs for doing that. We use LEDs to create light. But LEDs drop about 2 volts. Anything over 2 volts is considered a short. So I'm putting 5 volts on it, right? You understand? So what I had to do is size a resistor that would drop 3 volts, and then the LED comes on. You already know that. You just had that. So one polarity turns it on, one polarity turns it off. Well, this is what we have over there, because if I turn the magnet in this direction right here, it goes through a north and a south pole. So now I can come up here and do this, right? And it turns it off, and then when it moves across it, it does. See what I'm talking about? And that's basically what it's using over there. This is analog. So what it means, so this would be considered digital, right? You understand? So it either turns on or off. But you saw how complex it was, because the Hall effect sensor itself is an analog sensor. So what we do inside that thing, we have an analog to digital control, a single bit analog to digital converter. This guy it's just right out there. So it's going to give us a voltage. It's going to tell us what voltage. Sorry, this maybe we have to turn off to get it to come back on. And I've got it across my Hall effect. So right now it's dropping about half the voltage, the way this is designed. I'm going to start bringing a magnetic field in, and what do you start seeing it do? Here it's going up, right? I'm going to come over here, I'm going to flip it around and give it the other pole, and look what happens. It goes down. So one pole, it starts in the center, so it's like a voltage divider, right? And then one direction causes that output voltage to go up, and one causes it to go down. So technically with this guy, we could sense the strength of the field. So we could technically sense what? How close the magnet that we have attached to the thing that's in motion, how close it gets, would that voltage would indicate a position. Are we okay? This would be considered a proximity switch. When we say switch, anytime they say switch, limit switch, right? Photoelectric switch. Then these are digital devices. Right? You understand that? So we okay with that? Pretty sweet. Look at the size of these things. Now they can't conduct a lot of current, but the PLC, it only requires a few milliamps to trip the input. So, these guys would work great inputting into a PLC, but we wouldn't let it run much. This guy here, I've got it set up to, I think 10 milliamps. It's to turn I'm using 10 milliamps to turn the LED on. Rule of thumb, the maximum current in most LEDs is 20 milliamps. So you need to run it below that, but you need to have it so it'll come on. What's nice about LEDs though is once you turn them on, you can control their intensity by how much current flow you put on. So, the big thing now is I'm working on this guy. I had incandescent bulbs. You know what incandescent bulbs are, right? How do they create their light? Huh? Through a resistor, and a resistor is caught. But these resistors, these tungsten wires, we get them suckers so hot they glow white, right? Y'all understand that? Of course, that's why they blow all the time. Of course, what we try to do is go to fluorescent bulbs, but now the big thing is LED bulbs. I went out and bought an LED bulb for over my vanity in the bathroom, and it was 40 watt. It created the equivalent of 40 watts of light with 4 watts of power. So that means that thing consumes 1/10 of the power. So those things look like they might pay for themselves over a year. But they can, the big fluorescent lights, the big problem we have with fluorescent lights, we can't dim them. Right? You got to either have them off or on, but LEDs, we can do if you got a light dimmer in your house, you probably won't get all the way down to the bottom before they go up, but still you'll be able to dim those lights if that's the way you want it. So that's going to be predominant lighting before long. Everything's trying to move over because these guys will just about pay for themselves over a short span, right? I saw a ballpark that had LED lighting, and they would flash the lights to the music while it was playing. The big lights. LEDs don't care. The big old gas bulbs, what did they do? You ever been at a ballpark when they turn the lights on? How long does it take? Yeah, they gotta get all that gas warmer. They on and on and on. Yeah, you don't turn them things off. You got to do what?
You have to put a breaker for them.
Huh?
I think our school, they put a breaker.
Yeah, they got a big breaker somewhere. But you don't turn those things off and then back on because you got to let it. So y'all learned a little bit about light emitting diodes. You got to put them in the right polarity, right? You understand, or they won't work. And if you break them over, if you force them to conduct in the backward direction, you're messing up. Photoelectric sensors detects the presence of an object using what? Now you know these guys get power, right? So we have something that transmits light, and then we have sensors that can receive light. I think the example, I use this in my solid state class, is that that's all you're doing with these devices right here. You just transmit light. But what you're doing is it's pulsing at a certain, I'm covering this up so I don't, something like this. Of course, you can't see it. What can you see? Well, it's infrared. You can't see it. You can't see. We've only got a range of colors that we can see. If it's outside that range, we can't watch. So we see colors between infrared and ultraviolet. Between, not, we can't see ultraviolet, right? Right? We can't see infrared. But, so I have this would be an example of a transmitter of light. And up there in my projector, it's got a receiver. It detects light. And what it's doing is flashing different patterns. So if we was to look at it with the oscilloscope, you see one thing might be like this, the other thing might be like that, right? And then that thing interprets each one of those as either turn me on, turn me off, change the keystone, change this, change that, right? Which is pretty good. So, but what would happen if I come over here and did this? What happened? Okay, so now the receiver, so we can use that to sense an object, right? So if I've got a light being transmitted, and you see this all the time at your house, get out of the front of the TV, I can't change the channel, right? Well, what you've done is you sense their presence, right? You understand, because what they're doing is they're breaking the beam, what? Between you and your TV, right? And that's a sensor, so that's one of the main things we have. And guess what we call that guy? Through the beam. So some of them call it direct scan, but we'll teach you this through the beam. Pros, these guys are non-contact, they're solid state, so they have what? No moving parts. Cons, they require what? Plain environment, requires a power source, and they always drop a voltage, so you lose a little voltage through there. So we can hook these things, normally when we hook input devices up, we can hook input devices in series with each other, right? We would have a hard time doing it with these. Are we okay? So this is photoelectric sensors. They're going to mount somehow. We got to mount them, and we've always got to have a transmitter and a receiver of the light. Everybody okay? So the first one at the top, we'll call it, it's the through the beam. This is through the beam on the bottom. So how does it, so this guy's true all the time. So if we look at the PLC, this light would be lit, when there's nothing there. We come in, we break the beam, it'll go out. Right? You have to know that because the way you write your PLC program, you need to know what the sensor gives you back when it's true and when it's false. So this is what we just demonstrated with this guy right here. Right? And you've seen that demonstrated a lot of times. Anybody ever had to do that? Tell somebody to get out of front of the TV?
My grandma said your daddy was black.
Yeah, I've heard that too before. So, get out of the way. You're not made out of glass. See, they know. Odds are they know it's light. The other type we have, this is the ability to have the longest distance because the light only flows in one direction. The other two are shorter distances. We have the next one being the next longest distance. This is called retroreflective or retroreflective. So what we have is we have a retroreflector. A retroreflector, you see these retroreflective devices all the time. They can be made with beads. So normally when they make street signs, they'll paint them and then they'll pour the retroreflective stuff on top of it. And it's nothing but all these little glass beads. But what happens with a glass bead when you hit, no matter, as long as you're within a certain angle, if you come in and hit it, it's going to do what? It's going to bounce back to you, right? If it goes through the bead. Also another way they do is make these triangles, which you could probably see over here, what happens is it reflects a mirror. So if I had a mirror, what would happen when it sees light? So when can you see the reflection of a mirror? So what happens if the light hits it here, it's not going to go back to the detector, it's going to go over here somewhere, right? You understand? So, if we wanted to use this with a regular mirror, then the alignment of the mirror and the alignment of the transmitter would have to be perfect, right? Because if you was off a hair, then what would happen? It wouldn't bounce back to the source, right? Or if the mirror was slanted just a hair, right? It wouldn't do what? Well, what a retroreflector does, if it comes in here, it bounces back there over a viewable angle. And this is why you can see the stop on a stop sign when you're over here, right? You understand? Or you can see the red lights when you're over here, right? You understand? So we use a lot of retroreflectors. Inside most of your taillights have retroreflectors in it, so they can see your stoplight even if they're doing what? Because our lights are buried in a reflective surface, and they're back here. Well, what would happen is if I was over here, I couldn't do what? The light's going out here, right? You understand that? So what do they put on here? They put a retroreflective lens. So the light is coming out here doing what? Going off in an angle. So we use a retroreflective to spread the light over an angle, right? But we also use them to reflect light. So these guys, would they be true or false when there's no object there? They'd be true when there's no object. So it gives us the same thing as they threw the beam. It's just that the distance would be a lot less, right? Everybody okay? But what I do now is the transmitter and the receiver are in one unit. Are we okay? So this will be false when it breaks between the retroreflector and the transmitter, and it'll be true when there's not a part there. The last one we have is what we call the diffuse sensor. And what it's doing is it's depending on light being reflected off the object itself, which is the way we see, right? We see, but these are diffuse sensors. So what we're seeing is I'm not seeing you, I'm seeing what? I'm seeing the light reflected off you and the clothes you wear. That's the way we see. We've got cones and rods. I think the cones are the one that sees red, green, and blue, and then the rods see shades of gray. And between those four colors, we can see what? Any color. And that's why these displays work on the same principle. So that's our 3 photoelectric sensors that we were running through. We do have another one that's a variation of a diffuse sensor, and it's called a definite reflective, which I don't think I've got this here. So what the definite reflective does is it mounts the transmitter at an angle, and then it mounts the receiver at the same angle. So what happens is it'll transmit, and it'll hit the object, and then if the object is at the right distance, then it'll bounce back up and hit the receiver. If the object is not at the same distance, it's either going to miss the receiver over here, or it's going to miss the receiver over there. So definite reflectives basically sense a device or something that's at a precise distance or close to it. Okay. Anybody got any examples of that? A definite reflective. A mouse. A mouse uses a definite reflective. So if we look at it, we can actually see the angles, right? You understand? And I can come over here and get that sucker off this table just a hair, and nothing happens, right? You understand that? I can't do it with the camera. I can do this. So here's my mouse. I got it off just a hair, and it don't move. So this is detecting the impurities in that tabletop, but I got to be at a what? Certain distance, right? So this is called a definite reflective. Isn't it? So a mouse is an example of what we call diffuse. So it's depending on what? Reflective light, right?